Hello, my name is Dmitry Kaliada, and today we're going to talk about Elasticsearch. This is a free text search engine which has been created more than 10 years ago. There are a lot of forks appeared within this period of time. So they offer different flavors or different sets of functionality with focus on security or with focus on some other things like machine learning, log analyzer, and so on. But we would be focused mostly on functions related to free text search. So if you would have a look at Elasticsearch original website, you could find a lot of solutions based on Elasticsearch, such as site search, enterprise search, logs, metrics, some security case handling, and so on and so forth. However, for us, most interesting probably what the purpose of all these tools. So would these tools as in a complex offer as this amazing Swiss knife, or we would only stick in real life with such simple use cases, maybe in some case with different tool sets, however almost never with this Uber platform. So in reality, I would say Elasticsearch or ELK platform offer most useful components like Elasticsearch and Kibana. Elasticsearch as an engine and Kibana as a visualization tool. So sometimes for some purposes, some components like Logstash or other delivery or indexing mechanism could be used, but the core components, the core things, they are built around Elasticsearch, and Elasticsearch is a key and essential components of this ecosystem. So we wouldn't touch anything except Elasticsearch. We would be focused purely on functions, which makes this engine useful, popular, and we would like to understand the strengths and weaknesses of this engine. So before to go further, we need to understand, before to go deeper in engine internals, we need to understand basics of free text search, how free text search works in a nutshell. Text and search means we need to make text searchable. So we have some text and we need to turn them in some form which would allow us rapidly find some pieces of information. Text in Elasticsearch terminology named as documents. Documents could be big, like books, or small, like messages in this conversation. Every message in this conversation would be considered by Elasticsearch as a separate document. So, and further we would stick with this example to understand the basic principles of indexing and the querying of text. Let's make it searchable. First, let's take this text and make it searchable. So first of all, we need to take and execute 5 basic steps. Split text into the words, remove some noisy words, in Elasticsearch terminology called stop words. So this list could be edited and updated, depends on your needs, but in most cases, standard list of top words works pretty well. So as far as we take all noisy words out of our text, we can go further and on a step 3 extract roots of the words, meaningful part of the words. Again, we don't need any to store form of the words in different shapes. We need essential parts of them. As far as words prepared, number 3, it's finished. We've done with word preparation. Now we can start with gathering some statistics, counts, some maybe extra statistics. However, that's only we need to do, and count them, fetch statistics, and as a step number 5, store them into the storage. We would store them for our purposes, for our investigation purposes, in a simple table structure. However, in reality, it depends on the search, I would say, implementation. So it would be stored in special tree or some other form, which would improve search, which would give you advantages when you access this data. But for our purposes, we would just look at the basics in a table. So here we can see all our words has been stored in a table. Each of them has their ID, and as a third column, message ID, referred in which messages those words are appeared. So that's quite nice, and we can find them easily if we will start to use them. So all we just need to go, if we need to find the word, let's say pick, so we need to go in terms column, scan them, and find the word pick. So word pick would be in a message number 5, yes. So job done. However, it looks quite complicated, so we can improve a little bit this mechanism, and we could add word position. So once we add word position, then we can not only find, but also we can highlight this word in the message. So further, when especially if we are dealing with big amount of text, this type of information, word position, would be very useful for us, because it would allow us to exactly point what kind of information has been triggered our search engine to score them more relevant in comparison with other statements. Word position works nice. However, it's not the only thing which we can improve. So some words are more frequent, some words are less frequent, and in this case we can add an extra columns like count and frequency, and we can know what of the words are more popular, what is the less. And usually relevancy formulas, they give the priority to less popular words with lower frequency. So, and the more frequent words, they're not really highly rated. So later on we will see in query example, so how it works. And basically that's it. So we have some kind of structure and statistics around it. So basic index is ready. We wouldn't go into deep algorithmic implementation of such kind of structures. It's a different topic and quite big topic. So let's think about our index, like this way, and let's see what kind of other challenges exists in scope of free text search. And here we can start. We can step a little bit back in ancient times. Think about indexes as libraries. So we have huge amount of information which need to be structured somehow, which need to be turned into some useful things. This is an example of library, Trinity College in Dublin, one of the biggest libraries in the world. So, and what we can see here, this basic principles of indexing has been implemented hundreds years ago. So we should know how many books we have. We should know where these books are placed, which of them are more popular, which are less popular, to put them on the proper positions, to handle them better, and so on and so forth. And that's surprisingly, but those things are valid for our indexes, for our search engines. So we still need to think about volumes. We still need to think about access patterns, how quick we can get something, how big amount of data we can store without some issues, performance or space or whatever. So that's it. So we need to understand nature of our data, and to understand the nature, we need to start from our language. So how big index could be? This answer could be answered from analyzing how many words we are currently using, how many unique words could appear in our index, in our vocabulary. As per recent statistics, such dictionary, such vocabulary could contain around 20,000 words. So the same number we can get from another research regarding the newspapers. So, and 20,000 words looks quite common for modern language and modern people. However, we have more bright and outstanding example. 30,000 words has been discovered by researchers who analyzed William Shakespeare's works, and this is 10,000 words more than the average United States, than the average vocabulary of modern people or modern information sources. So 30,000, it looks big enough, and it not really not easy to handle for single human. However, for modern hardware, we can estimate such index could fit into the 600 megabytes. So assuming one word, in average one word contains 5 characters, and one character, it's 4 bytes per character. So 600 megabytes, it's not so big to fit into the memory and then scan or compare or do whatever we like to do, especially with efficient structures. Of course, English language cannot be considered as the most complicated or difficult. There are other languages, however, the numbers would not change it like drastically, so we would still have more or less similar amount of statements. And bigger challenges right around the corner, they came to us together with informational technologies. Our phones, for instance, just pool of phone numbers in the world, 3.2 billions numbers, quite big, 3.5, or IT network devices, more than 75 billions different items. So this looks big, and it would require special ways of the handling. However, we have another source of information, is a time, which is comparable, like two years of in seconds, comparable with all Internet of Things devices. So, and this is just in a second. So if you would switch to some processes which require bigger precision, such as nanoseconds or milliseconds, we would turn ourselves into bigger dimensions, which is required very careful attention and very proper handling. So and that's why. And if we would compare with our reference 30,000 words, so phone numbers 100,000 times bigger, Internet of Things devices 2.5 million times bigger, and time in nanoseconds 1 billion times bigger. So we wouldn't be able to fit this into a memory of normal computer, never, of at least at modern computer. So, and it would require special data structures, it would require special ways of handling. Having this in mind, we always need to think, when we're estimating the index sizes, when we think about indexing, we always understand the nature of data and use cases around this. So if, let's say, our time came to us in milliseconds or nanoseconds, but for search purposes or for some other purposes, we are using days or months or years, so we don't need to keep this level of precision data into the index. So we can keep this in database, we can keep in some other place, so but never in index. Index need to have only essential data, only valuable data which would help us to reach our goal as fast as possible. So it need to be always validated, need to be think twice before keeping such type of precision or such type of data statements into the index. Or for instance, some hash data or some obfuscated data which like meaningless, and it would never repeat it. It would just saturate your index. If such kind of cases need to be handled in your system, think about handling this in with some other tools like databases or some other engines, not in index. So that's it about data, and we can talk a little bit about Elasticsearch implementation principles. As I mentioned, Elasticsearch has been created 10 years ago, and it was built based on the Lucene engine. At that time, there are other popular framework was around, Solar. It still exists till now, but it not so popular as Elasticsearch because of the some patterns of management and handling, quite old-fashioned. Some engines, some solutions are built based on Lucene or based on Solr, but for now, Elasticsearch looks more scalable, more preferable. So the basic principles are the same. So we have dictionary of terms, we have documents, and they stored on some hard drive or SSD or whatever, which allows them to be placed properly and accessed properly. So the major principle of handling such type of data structures called sorted string tables or SS table. The same principle taken into the other popular solutions like Cassandra, HBase, LevelDB, React, and so on. And it works pretty simple. So in ideal cases, so we need to have one solid file and structured file which contains all our data, all our statements, and we would be able to easily navigate and find the word and some document on top of this. However, we cannot turn all our dictionary, like our active dictionaries, in a single file, because it may take 5 to 20 gigabytes per such file. And in case we need to add something or update something or delete something, this would cause big impact on performance. So for those purposes, levels introduced. So several levels, and the lower level contains some big segments, big files. The higher levels, they are almost atomic. They contains few statements, few documents. So, and what it gives us ability to for frequently change the data. It would be always sit in on higher levels, and data would be populated in these segments, then merged on deeper segments, and so on and so forth. And at the very end, these segments would be promoted to one big solid segment with rarely changed data, with almost perfect data structure. So this works well. So except the cases when you need to change or delete from these big segments data occasionally, or not occasionally, or on purpose. So in this case, the actual erasure operation wouldn't happen. This data would be just marked as deleted, but still exist in an index, and fresh data or newer data would be written into lighter segments on upper levels to be handled like on a proper way by the engine. So these old segments later on might be deleted or might be cleaned during the merge procedure, but such procedure happen quite rarely. Depends on some conditions or settings of the engine. So I just let's wrap it up. So ideal case, one big solid file. So frequent updates do not allow us to keep all data within this one big solid file. And so for these purposes, we have multiple levels with smaller segments which could be updated more frequently. So these segments could be merged back into more efficient data structures later on, based on the some manual or automatic rules for this engine. So let's return to our initial table, initial index. This index contains a dictionary with identifier of positions, terms, messages, count, and frequencies. So what should we do? What steps should we perform to make this query execute? There are 5 simple steps, and they are valid for most of the queries. So first of all, we are getting to simple step of tokenizations. We are splitting the phrase into the words, and in our case, it's just 2 words. Then these words need to be normalized. Again, in our case, normalization quite simple, just lowercase. That's it. So we may start our search procedure. During this phase, so we are fetching the we go to our index and fetching the information about those terms for the over and here. So once you've got this information, now you can calculate relevancy. So relevancy means which document would be highly ranked, which document would be like with a lower rank. The answer quite simple in our case. So document number 4, which contains terms over, would be ranked higher because of the frequency lower, and it exists only because the frequency is lower. So the other 2 documents, they would be joined as with lower rank to the search response. That's it. So how the engine works. But of course, the real formula would looks like maybe in some cases more complicated, but the basic principles remain the same. So we have the words, we have statistics, then based on the words and statistics, we are calculating the result and sending back to the user. Type of the queries. Single word query is the simplest type of the query. So it's exact string matching. So we have one string and another string, comparing them, and if they exactly match it, this is our candidate. If not, then we need to do something else. So the second is a phrase query. Phrase query more how to say, friendly for text, for language, for human language, because it allows us to be more flexible, extract roots of the words, consider position of the words in the phrase, and rank the results based on the sequence of the words of the phrase. It's much more powerful and should be used in cases when we deal with human languages. So the other types they called wildcard. Wildcard queries could be useful. However, it is not really recommended to use them frequently because they required a lot of resources, computational resources, and sometimes they could cause significant performance impact on entire cluster. For instance, the last one, wildcard prefix query, could cause long execution and scanning of multiple files and indexes in the engine, and it would affect the performance not only of this single query, but also performance of other queries of other users. So ideally, to avoid such kind of queries in your solutions, however, if it's required, sometimes it is really required, so it needs to be handled very carefully. And ideally, wildcard prefix queries implement some other ways to avoid Elasticsearch native like direct query and Elasticsearch direct mechanism. The other part, so we need to analyze if we need to understand how to what would be price, what would be cost of indexing documents, how we need to be prepared for indexing, what Elasticsearch, how Elasticsearch could help us to do this more efficiently. Before we move forward, this is single index in Elasticsearch terminology called shard. So later on we would call this single unit of data, single index shard. What for this shard, what we need to solve: the write speed, read speed, capacity, and high availability. Let's evaluate what is the state of the things for one shard. And in this case, we have a limited write speed, limited because we have together write and read. We have limited capacity because this the only logical unit we can access. And in terms of the high availability, this is a single point of failure if something happened with this shard. So our index would be not available. We would not be able to use it anymore. So for these purposes, Elasticsearch offered us concept of data segments. So we have our shard, we've split them into several shards, which turns us in multi shard configuration. So what kind of questions we've solved here? So we've increased write speed, we've increased read speed, and we've increased capacity, because these segments could be placed on different drives. They could be placed even on different servers, even in different data centers. So, and it gives us a much more flexible solution. However, we still don't have high availability, because those segments exist in one copy. So easy answer, so we need to add more copies, right? So for each index we've added an extra replica. So now we have redundancy, now we have high availability. So if one copy goes down, another copy take over, and it not only take over, but Elasticsearch will trigger to create an extra copy to keep your copies always at the same level of replication. So that this mechanism works pretty fine, and you may give a lot of copies for your data. For instance, for read purposes, for some region-based or reg-based data protection policies. And if you need to improve read performance or add more storages, or take all your data in more safe access patterns or safe places. So all the things are in place. And let's see what's happening with writes and what prevents them to be such efficiently scalable as other operations. So first of all, so when we work with data, we are writing always to a primary shard, to a single shard, which is called master shard or primary shard. So, and once the data hits these shards, it's indexed and stored on them. However, it not exists on replicas. It not exists on in other places. So, and we need to populate replicas then. So from primary shards, the data goes to replicas to make them in sync, to make them synchronized. And the thing is, so population of replicas, it's not just a data replication, it's a complete reindexing. So every replica built her own index from the beginning. So the initial shard just populates the data, just feeds the data. However, replicas, they may have their own way of data control. So let's say we are doing this reindexing job as much times as we have replicas in our cluster. Let's say if we have 3 replicas for shard A in our cluster, so then we need to perform index 3 times. And of course, for indexing, we always need to think about this, to allocate enough computational resources and enough storage related resources like I/O and space to handle this data. And what's also important, this type of, as far as we have as per our as far as we have as per our image like 3 replicas, so every replica would require a dedicated data flow, which would trigger additional load, additional network load. So we need to be sure so network would be able to handle this data and wouldn't stuck in place. Elasticsearch, by the way, offers some mechanisms of handling this, of control, how fast and how hard network would be pressed. By default, the limits are quite low. So in some cases, if you need to improve your replication speed and your network quite capable, you can up these limits and do it faster. So we finished with indexes and with indexing and the principles how the shard works. Let's see a little bit how cluster works itself, what is the cluster topology, what kind of roles we have, and how we can properly manage our setup to be efficient and performant. So there are a lot of roles mentioned on Elasticsearch website. However, we can stick with more basics, more important. I wouldn't say they're more important, but they are essential. So for the cluster, so master nodes, coordinating nodes, and data nodes. When you just install Elasticsearch, when you install Elasticsearch without any special configuration, you just download from the site and install on your machine. So your nodes would be 3 in 1. They would be master and coordinating and data node in one. So, however, it works for development and maybe some other purposes, but for real life production purposes, such configurations are not really capable, and they're not recommended to use as like 3 in 1. The roles need to be dedicated. So it it's easy to do. So when you start your cluster, either as a command line parameter or as environment parameter or as a configuration file parameter, you need to specify the role for your node, for master, for data. If no roles specified, so your instance, this instance would be considered as a coordinating node. So let's see what every role is doing in the cluster. So the master is in charge of cluster consistency and synchronization. So it just works as a coordinator, as a manager, to track the indexes, index names, aliases, any type of service data, nothing related to actual documents handling. It only only information related to the index state and consistency. So for these purposes, you need to be aware about the split brain situation when you might have some master like inconsistent information between master nodes. For these purposes, you need to define quorum. So how many master nodes are required to change decision or to change of cluster state. If quorum not exists, so we are considering our cluster not in sync, not synchronized. So and new master nodes need to be added in order to fix it. So another one role is data. Data actually consists all our indexes. It contains all data. It contains all index files. And if you also keep an actual documents together with indexes, it also would contain these data files. So it most the heaviest nodes in the cluster, they require most of the resources and they do all the job, indexing job and like query handling job always hit these nodes most. And the other role, sometimes this role not taken seriously, but in most cases it's very useful. So coordinated nodes, these nodes could be considered as endpoints, access points to a cluster. So instead of the sending queries, especially search queries directly to data or master or whatever nodes, so you can point these nodes and they would be handling of query processing. So if you would require special merge of aggregations or post processing of responses which get back from data nodes, this node would take care about this. So and this node quite useful because it allows you to remove such some post processing from out of the data nodes and keep data nodes only dealing with their data which they are in charge, which stored in their indexes, and do not do any extra post processing and aggregations. So if you would have a look at the number of nodes in the cluster, recommended numbers, so for the normal handling or for the normal processing, ideally to have at least 2 master nodes, at least 2 data nodes, just to have some replicas of your data, but ideally to have them like bigger amounts of resources dedicated for these purposes. And one important thing for master, better to keep these master nodes on dedicated host to avoid like any overlaps with data nodes or coordinating nodes. If something happened on these nodes because of heavy indexing processes or heavy query processes, so it might affect the master, and if masters not respond in a time, or if masters cannot get response from some other nodes, the cluster state could be turned into inconsistent position. So better way to keep masters as dedicated hosts, and it would prevent any unnecessary cluster state changes. So again, for masters, it also easier to take them in separate nodes because of they do not require too much resources. Here is upper bound I've mentioned for masters to dedicate for them. However, they may have less RAM and less cores if your index is not so big, not so huge. So, however, for data nodes, you need to allocate much more resources, especially CPU, because indexing and query processing procedures, they require quite big amount of CPU cycles burned, and of course disk and network. Data nodes, they data intensive, they populate and they consume a lot of data. So for these purposes, you need to supply them with good performance storage. Ideally, of course, to use solid state drive storages. However, there are a lot of examples when hard spinning disks and turn it into the RAID 10, they perform well, and maybe they could, in some cases, could outperform SSDs. So again, it's up to you, up to your hardware, up to your configuration. For coordinating nodes, disks not important. You just need to take care about memory and network, because network node or coordinating node would distribute query to other nodes and collect back result and computate final result based on the response. One important thing to mention regarding the memory, like you see for the data node, we have upper bound of memory 32 GB RAM. In reality, it might be even 31 GB, and it relates on Java, how Java works. So if you give more amount of RAM to nodes, it would perform at some point not so well, so because of the internal Java mechanism. So ideally, to keep these data nodes with up to 32 GB of RAM, and it, as practica shows, it real life example shows it gives quite nice results for real life use cases. So we are getting to the end of our presentation. So let's see again. Let's name again what is the strengths and weaknesses of Elasticsearch we have. So the free text search capabilities is a key point. So if we work with natural language sources, if we work with some like high semi-structured or structured sources, so this engine would give us nice capabilities to handle such type of load. So also as a pleasant bonus, we may have a competitive geo search capabilities. So yes, we cannot consider Elasticsearch as a outstanding geo search engine, but some geo queries could be easily handled. So the special mechanism has been designed. Again, high availability, easy to configure, easy to maintain. So very reliable and stable engine. So with the proper approach and absolutely brilliant horizontal scaling, you can build cluster up to you can build cluster and then cluster of clusters and handle huge volumes of information. So, and like build your own Google if you wish. That's easy with proper approach. It would require some tweaks, of course, but it's possible. So, and regarding the limitation, there also exists the query syntax quite exotic. In some cases, in some engines, they offer special wrappers which offer SQL based interfaces. However, native queries and native syntax cannot be completely substituted by SQL because it contains a special construction and special way of query handling. So dataset joins. So dataset joins one of the biggest disadvantages. So indexes, they're not designed to handle joins. They trigger a quite big something similar to joins could be implemented, but it required big resources and do not work smooth on any type of data. For joins, better to use engines like RDBMS, Postgres, MySQL, Oracle, and so on and so forth, but not Elasticsearch. So counts and statistics, they exist, but they are not accurate, and they are quite expensive in some cases, especially if your dictionaries are big. So you need to think about this multiple times. So, and expensive and not accurate. So you can get wrong data and pay for this like huge price. I mean, a huge price in terms of computation resources. So regex driven queries, all these wildcards, they are very expensive. So again, it's not what need to be ideally implemented based on Elasticsearch. Ideally to have some other mechanisms of implementation such kind of queries. And the fifth point, it's virtual consistency. The data might be populated in one shard but queried from another shard which has not synchronized yet, or data has been populated in a shard but not exposed yet. So there are a lot of cases which says this is a bad synchronization point. For this purpose, it's better to use dedicated and more predictable mechanisms. So, and out of the box capabilities good. Elasticsearch quite capable with default settings till the moment you are following the recommendation and you are not hitting the limits recommended by the vendors. So if limits are broken, so you may find significant performance impact on the engine. So, and this is the limits. So recommendations almost universal for any cases. So shard sizes and number of nodes per cluster, shards per cluster, fields per index. So all of those items need to be carefully managed. So if you have some cases which require to broke this recommendation, better to think number of times before doing this. Otherwise, you would not predict what cases or what kind of statements might trigger the performance impact or some unpredictable cluster state. And what important, if such limits crossed, so cluster recovery or cluster recovery or cluster stability control mechanisms would perform not so efficient as they could be with having these limitations in mind when you're designing your cluster and indexes. Sometimes you can split indexes, sometimes you can split clusters, you can have multiple clusters for different purposes and then cover them with another cluster. There are multiple options. So if you have such challenges in your project, better way to think how to split this in some efficient way. So that's it. Thank you for being here. If there are any questions you have, just let me know. I would be able to answer in person, or we can record the new live sessions for education purposes. Take care. Bye bye.